All right, welcome. Today we are tackling a real classic from the I.E. Irodov collection, problem 1.21. Now, if you've ever picked up this book, you know these aren't just plug-and-chug problems. They're designed to make you really think about the physics.
Okay, let's just dive right into the problem statement. So, we've got a particle leaving the origin at time 0, moving along the x-axis. And here's the kicker. Its velocity isn't constant. It changes with time according to this function. So yeah, this means we've got to be super careful. We need to figure out, where it is at certain times, when it's at a certain spot, and the total distance it's actually traveled. The whole shebang.
So here's how we're going to break it all down. We're going to go step by step. And trust me, the most important part is coming up first. We need to understand what this particle is actually doing before we even think about writing down an integral.
All right, first things first. Before we jump into solving anything, what do all good physicists do? They get organized. Let's pull out all the information we were given in the problem.
So here are our tools for the job. We've got the initial velocity, v0. We've got this time constant, tau, which, seems pretty important. And then we have the rule, the function that tells us the velocity at any moment in time. Honestly, this function right here, that's the heart and soul of this entire problem.
Okay, so before we get all excited and start doing a bunch of calculus to find the position, let's just pause. Let's take a step back and ask a really simple but incredibly powerful question. I mean, what is this particle actually doing? Look at that velocity function. It's clearly not constant, right? As time t gets bigger, that fraction inside the parentheses gets bigger, which means the whole term in the parentheses gets smaller. So the particle is slowing down. But what happens if t keeps getting bigger? What happens then?
You see, that's the absolute key. At some point, the velocity isn't just going to be small, it's going to hit 0. And what happens then? It reverses direction. Finding that exact moment, that's the physical insight that unlocks this whole thing. And it's simple enough to find. We just set our velocity function to 0 and solve for t.
And boom, there it is, 5 seconds. At exactly 5.0 seconds, the particle just stops for an instant. And for any time after that, its velocity goes negative. It starts moving backward. I'm telling you, this turning point is everything. It's the key to getting every single part of this problem right.
Okay, so now that we have that critical piece of physical intuition, the turning point, now we can start calculating. We want to find its position, right? So how do we get from velocity to position? Well, that's a job for one of our favorite tools in kinematics, the integral. The position function x of t is just the integral of that velocity function.
And when we do that integral, this is what we get. This neat little equation right here gives us the particle's x-coordinate, its displacement from where it started at any time we want. So now we can finally tackle part A of the problem. Let's plug in some numbers. At 6 seconds, so just after it turned around, it's at 24 centimeters. Cool. Now at 10 seconds, wait, it's back at 0. It returned to the origin. And by 20 seconds, whoa, it's way back at negative 200 centimeters. This completely confirms what we figured out earlier. It went out, it turned around, and it came all the way back, past where it started.
All right, on to part B. This time, they're flipping the script on us. We're not given the time, we're given the position, and we have to work backward to find out when the particle was at that spot. So yeah, we're going to have to solve that position equation for t.
Now, hold on. Here's one of those classic physics problem traps you have to watch out for. Read the question carefully. It asks for a distance of 10 centimeters from the origin, not a displacement. What does that mean? It means the particle could be at positive 10 centimeters or at negative 10 centimeters. We have to check for both. And check this out. This is a perfect example of why finding that turning point was so important. When we solve the math, it's a quadratic equation, we get not 1, not 2, but 3 different times. Think about it. It passes 10 centimeters on the way out, then it turns around and passes 10 centimeters again on the way back, and then it keeps going, crosses the origin, and hits negative 10 centimeters. 3 different moments in time. So cool.
This whole thing leads us right into a really fundamental concept in kinematics, one that this problem illustrates perfectly. And that's the all-important difference between distance and displacement.
So, remember, displacement is the shortcut. It's just where did you end up compared to where you started. But distance, that's the total path you traveled. It's like the odometer on your car. So for part C, when they ask for the total distance covered, we can't just blindly plug a time into our position formula. No way. We absolutely have to account for that turnaround.
So to figure out the total distance at 8 seconds, we have to split the trip in two.
First, there's the journey out to the turning point at 5 seconds. We calculated that position. It was 25 centimeters. Then, we need to figure out how far it traveled back between 5 seconds and 8 seconds. And that's just the difference in its positions, which turns out to be another 9 centimeters.
So, you add those two legs of the journey together, the 25 out and the 9 back, and you get a total distance of 34 centimeters. And see, that's way bigger than its displacement at 8 seconds, which was only 16 centimeters. It just makes perfect sense when you actually picture the particle's entire trip.
Okay, to wrap this all up, let's visualize it. Let's see what a plot of the total distance traveled over time actually looks like.
This plot really tells the whole story, doesn't it? For the first 5 seconds, you see the distance growing as the particle moves away. Then, at 5 seconds, it hits that turning point. And after that, even though the particle is moving backward, the total distance traveled just keeps on climbing. It has to, right? The odometer on a car never goes down. A distance plot can never have a negative slope.
So, before we finish up, just think about it for a second. What was the single most important step in cracking this problem? Was it the calculus? Was it solving that quadratic equation?
No, the real key wasn't the math. It was understanding the physical story first. This particle slows down, it stops, and it reverses. That's the big takeaway. Before you ever start plugging numbers into formulas, you have to visualize the physics. Realizing there was a turning point at 5 seconds, that was the one thing that made everything else just fall right into place. And that, my friends, is how you go from just solving a problem to truly mastering it.